Hi guys, in this lecture I will be discussing about the problems related to geometric design of the track. So before moving to the problems related to geometric design of tracks, we have to be well versed with some of the concepts related to geometric design. So even though we have discussed these concepts in the previous lectures, I want to re-embrace these concepts, that is equilibrium cant. What is equilibrium cant? Equilibrium cant, we are going to repeat this word repeatedly in the problems. Equilibrium cant is nothing but the super elevation, and you have to study what is cant deficiency, negative cant, general procedure to solve the problems, and limits of super elevation and cant deficiency. These things we have to discuss before moving into the problems. So we will look what is super elevations. The super elevations, we have established these things in the derivations itself. The super elevation, or E is equal to 1.676 V square divided by 1.27 R. So these things we have discussed. For a broad gauge track, this is valid. For a meter gauge, for a narrow gauge, these things are valid, right? This is equilibrium cant. So coming to the cant efficiency, definition of a cant efficiency. Cant efficiency may be defined as the difference between the equilibrium cant, that is nothing but a super elevation necessary for the maximum permissible speed on a curve, and the actual cant provided. Actual cant is nothing but a super elevation provided. So this is the cant efficiency. Moving on to negative cant. Negative cant is nothing but equilibrium cant minus cant efficiency will give a negative cant. Theoretical cant. Theoretical cant or theoretical super elevation is nothing but equilibrium cant plus cant deficiency. This is how we are going to get the negative cant and a theoretical cant. So moving on, limitations of cant deficiency. So you cannot give the cant deficiency, or you cannot give the cant as your as your wish. There are certain limitations that you cannot provide the cant deficiency exceeding some of the numbers which are given in this table. The maximum value of cant deficiency prescribed for Indian Railways is as shown in the following table. The cant efficiency for speeds up to 100 km per hour for broad gauge tracks, meter gauge tracks, and narrow gauge tracks. And for a broad gauge track, it should not exceed more than 7.6. For a meter gauge track, it should not exceed more than 5.1 centimeter, and for a narrow gauge track, it should not exceed more than 3.8 centimeters. And coming to the high speed tracks, for a high speed tracks, it is nothing but speeds which are exceeding more than 100 to 120 kilometers per hour. That is for a broad gauge track, it should not be more than 10 or 10 centimeters, right? These are some of the limitations of cant deficiency. Moving on, you can see some of the you can see a derivation in this slide. You need not worry more about these derivations. What you have to take from derivations is what is this radius or degree of the curve. How do we calculate the degree of the curve? Degree of the curve is given by 1720 divided by r, right? You have to be more worried about this equation, that is d is equal to 1720 divided by r. So this is required for us to calculate the radius. R is equal to 1720 divided by d. So these things we have already discussed in the previous video which you have prepared. You need not worry more about these derivations. So let us look into next concept, that is what general procedure. The method of working out the speed on main line, branch line, and negative super elevation on branch line will be clear from the following steps. The equilibrium, super elevation or cant on both branch line is calculated by the formula. So in this case, the branch line is most of the things branch line is specified for the railway track. When it is deviating on a curve, it has to be split into two halves. The main track is one which continues from the previous continuation. The branch line is one which is taking the deviation. The equilibrium, super elevation or equilibrium cant on branch line is calculated by the formula given by equation 5. Equation 5 is nothing but which we have already discussed in the previous slides. This is the formula which we are going to use for calculation of equilibrium Kant. E is equal to 1.6. That is a formula which we are going to use for calculating the equilibrium super elevation. The permissible Kant deficiency is deducted from the equilibrium Kant as obtained in step 1. Next, this we are going to I am going to explain you in the problems itself. The difference obtained, that is equilibrium Kant minus permissible Kant deficiency, will give the negative super elevation to be used on the branch line. The negative super elevation is also equal to the maximum super elevation permitted on the main curved track, right? The restricted speed on the curved track is obtained by adding the permissible deficiency in maximum Kant on the main track and applying the formula phi. Formula phi is nothing but I showed you in the previous slides. So these are some of the limitations of Kant deficiency, limitations of super elevations and Kant deficiency. So these formulas are very important. You have to go through these formulas in order to solve the problems related to the geometric design of a track, right? So the maximum permissible super elevation for a broad gauge track is 1/10 the gauge. This is the broad gauge track, the measurement of a gauge for a broad gauge track. This is meter gauge and this is narrow gauge. So let us start with the problem itself. A 5-degree curve diverges from a 3-degree main curve in reverse direction in a layout of a broad gauge yard. If the speed on the branch line is restricted to 35 kmph, determine the restricted speed on the main line. It has been given. We have to determine the restricted speed on a main line. We have the curvature for a diverging curve and a curvature for a main curve is given. Main track is given. So what we have to do here is we have to consider the super elevation on diverging track. So we have to calculate the super elevation for a diverging track. So how do we calculate? We have to consider the formula E is equal to GV square divided by 1.27 R. This we know from the previous derivation, where G is for a broad gauge track. It has been given to us as a broad gauge track. For a broad gauge track, G is equal to, that is gauge length is equal to 1.676 meters, and V is equal to, it has been given to us if the speed on the branch line is restricted to 35 kmph. The speed is restricted to 35 kmph, hence we are going to consider V is equal to 35 kmph and R is equal to 1720 by D. This we have looked in previous slides. D is equal to 1720 divided by R. That is what we are going to consider for that is a degree of curve. We are going to consider degree of curve. D is equal to 5 because it has been given a 5-degree curve diverging. This degree which is given is for a diverging track, hence we are going to consider D is equal to 5. So by substituting all these values in this equation, we are going to get E is equal to 4.71 centimeter. So the negative Kant is equal to, so how do we get this negative, what formula? The negative Kant is obtained by the difference between the equilibrium Kant and the Kant deficiency. So equilibrium Kant, that is nothing but a super elevation, E is equal to 4.71 minus Kant deficiency is nothing but Kant deficiency is, how do we get this Kant deficiency? 7.6. So in order to know this, how do we get this? We have to go back to the table. Go back to this table. So the Kant deficiency is given for a broad gauge track is given as 7.6. This is available in the textbook. You need not worry about these things. But one thing you have to be careful is this table will not be given in your examination. So you have to be careful about this. This table will not be given in your examination. You have to remember these values, right? You have to remember these values. Let us move on to the problem. So negative Kant is equal to equilibrium Kant minus Kant deficiency. The equilibrium Kant is obtained as 4.7 from the above calculation, and Kant deficiency is 7.6 for a broad gauge track. Hence we are substituting the Kant deficiency for a broad gauge track as 7.6, which from which we are going to get negative Kant as minus 2.89 centimeter, because the cant efficiency for a broad gauge permitted is equal to 7.6 centimeters from the table. So negative cant is equal to maximum permissible super elevation on the main line. So what is the maximum permissible super elevation on the main line is equal to 2.89 centimeter. So negative cant is equal to maximum permissible super elevation. You have to be careful about this. I have told you in the general while explaining the general procedure, that is negative super elevation is equal to the maximum super elevation permitted on the main curved track. This I have explained you. Next, moving on, the theoretical super elevation which can be provided on main line is equal to 2.89 plus 7, that is equilibrium cant plus cant deficiency. That is, we have looked upon this in the beginning itself. That is, theoretical cant is equal to equilibrium cant plus cant deficiency. That is, hence we are going to get theoretical cant as 10.49 centimeters. Hence the speed of the main track can be calculated from the formula of equilibrium. Super elevation is equal to gv square divided by 1.27 r. Super elevation is equal to 10.49, which is equal to 1.676 into v square into 3 divided by 1.27 into 1720. Therefore v is equal to 67.4 kmph. So the restricted speed on the main track is equal to 67.4 kmph, which can be equated to 65 kmph, right? This is how we can solve this problem. Hope you have understood this problem. Let us move on to our next problem. I have taken an example of the problem number 6 in your textbook, that is Aurora and Saxena. So what would be the permissible speed on the curve if on a 8-degree meter gauge track the average speed of the different trains is 50 kmph and the allowable cant efficiency is half that of the maximum cant efficiency? So it has been given to us. Some conditions have been given to us. What we have to do here is what would be the permissible speed. We have to calculate the permissible speed on the curve, right? We have to calculate maximum permissible speed on a curve. So in order to do that, what we have to do here is we have to consider the equilibrium condition for a equilibrium cant condition for a meter gauge track. For a meter gauge track, in the beginning slides I have explained you, for a meter gauge track equilibrium cant is given by 0.80 v square divided by r centimeters. So that is what has been considered here, right? Equilibrium cant for a meter gauge track is equal to 0.8 v square divided by r. Substituting the value of v and r, this is 17 r I have got by 1720 divided by 8, which has been given as degree of curvature as 8 degree. So the same value is written here, that is d is equal to 1720 divided by r. The same equation is taken here. So by substituting the values, I have got a equilibrium cant as 9.3 centimeters. The maximum super elevation is equal to 1/10 of the gauge. In this case, the gauge is considered as a meter gauge. We know that measurement of a meter gauge is the distance between two rails is about 1 meter. That is what the meter gauge is. So I have considered the meter gauge as 1 meter. Hence, by substituting the values, I have got the maximum super elevation as 0.1 meters, that is equal to 10 centimeters. The maximum theoretical cant. The maximum theoretical cant is given by maximum cant plus cant deficiency. Maximum cant plus cant deficiency. Maximum cant is 10. It has been taken as 10 here instead of here maximum cant. We have got the maximum cant as 10 centimeters. So cant efficiency is given by in the problem itself they have given as the cant efficiency is half of the maximum cant efficiency. The maximum cant efficiency is 5.1. How did I get this 5.1? From the table, right? For a meter gauge track, in this table you can see here the cant efficiency for a speed up to 100 kmph. For a meter gauge track, the cant efficiency is 5.1 centimeters. So I have considered the maximum cant efficiency as 5.1. So in the problem it has been given to us the cant efficiency is half of the maximum cant efficiency. The maximum cant efficiency is maximum allowable cant efficiency. The cant efficiency is half of the maximum allowable cant efficiency. Hence I have got the values 2.55 centimeters. So the same thing is explained. This I have got the cant efficiency for meter gauge track as 5.1 from the table, 5.1 centimeters from the table. Therefore maximum theoretical cant is equal to maximum cant plus cant efficiency. So you should not substitute the value of maximum cant efficiency. You have to substitute the value of the cant efficiency, not the maximum cant efficiency. So the maximum you have to consider, in order to find the maximum theoretical cant, you have to consider the maximum cant plus cant efficiency. Maximum cant is taken as 10 centimeters. From how did we get this 1/10 of the gauge? From these limitations, right? From these limitations I have got the maximum super elevation for maximum cant for meter gauge as 1/10 of the gauge. 1/10 of the gauge. The same thing is substituted here. Therefore the maximum theoretical cant is equal to 10 plus 2.55 centimeters. 2.55 is the cant efficiency and 10 is the maximum super elevation. Hence I have got the value of maximum theoretical cant as 12.55 centimeters. Hence the maximum speed corresponding to the theoretical cant V is equal to square root of 12.55 into 1720 divided by 0.8 into 8. It is equal to square root of 3370 and V is equal to 58 kmph, right? According to the formula of speed given by the railways board, Vmax is equal to 4.35 square root of r minus Vmax is nothing but maximum allowable speed. Vmax, these things I have given you in the notes itself. This is also very important in order to solve the problems. This V I have got from the theoretical cant formula, that is V is equal to square root of E into R divided by 0.8 and Vmax is equal to 4.35 square root of R minus 67. This is a very important formula. By substituting each and every values, I have got the maximum allowable speed as 52.7 kmph. You can equate it to 52 kmph. Therefore, the maximum speed permissible will be 52 kmph. As the average speed of the train is 50 kmph, the maximum speed allowable is 52 kmph, which is more than the average speed. So no speed limit signboard is required. So you need not worry about these statements. Just calculate these values. That is, what is the maximum speed allowable. You have to design until this Vmax, right? Hope you have understood the concepts. Thank you.